light as possible. Kindly bear with me. So this topic, robust conic satisficing, is joint work with my advisors, Melvin and Napat. And Minglong has already introduced the topic for me, so it's kind of already set the stage. So I'm just going to take it ahead to the conic framework. So robust satisficing was something which he explained, but I'll just quickly take you through some basics. So the nominal problem is something which is fragile because it doesn't take into account uncertainty. So basically, we're trying to minimize C transpose X subject to G of X Z hat, where Z hat is the nominal parameter, deterministic nominal parameter, less than or equal to 0 for some X in X. So this problem typically, because it does not take into account uncertainty, it's fragile and the solutions cannot really be realistic in nature. So robust optimization, since the last 2 decades has tried to address this by fashioning an uncertainty set. So, okay, you take into consideration uncertainty, but you make it live in a ball. So it's a norm-based, or in general, a convex penalty-based uncertainty set. So here, the PZ here is a convex penalty function, and the uncertainty lives in a ball around this nominal value Z hat. But the problem again is that it's conservative, and you're not taking into account uncertainty beyond a certain point. And we know that it hugely depends on the nature of the constraint function as well as the nature of the uncertainty set. The tractability would depend on these 2 factors. So as Minglong had explained, so robust satisficing, basically what it does is it allows nature to take its course and allows the uncertainty to vary over the entire uncertainty support, which you see the calligraphic Z here. So instead of restricting it to an uncertainty set, it allows the nature to vary over the entire support. And of course, this comes at a cost. And the cost is that we need to allow some degree of infeasibility. So that is captured here. So to the extent the uncertainty deviates from the baseline value, so we have this K, which we'll call as the robust satisficing parameter, or you can think of it as fragility. So we try to minimize K, and in that way we minimize, or we rather have a control over the level of infeasibility here. Sorry. Yeah. Now, of course, we also have to trade off with the optimality, and so that's why you see this over here, the C transpose X less than or equal to tau. So basically, this comes from the concept of satisficing first proposed by Simon. So where so you have a certain aspiration level. Instead of saying that I want to, let's say, just see profit as something to be optimized, I look at profit as something which I just want to attain some level of profit, and then I focus on other goals. Or for that matter, the cost, I just don't want to minimize the cost, but I want to be within a certain level of cost. So the concept of satisficing it goes back quite to the 1950s, but now this is applied in the robust optimization framework. Now, so just to kind of give a pictorial example, so it's like going out in the, especially in Singapore weather, could rain at any time. So, we don't account for the uncertainty, then we're going to be in trouble. But you could account for a little bit of uncertainty, maybe for myself, and just protect myself, some part of my body from the rain. Or I could have a more holistic kind of protection. So this is like from the protection point of view, where not just myself, but I could protect many others when I take more uncertainty into account. So now, at the heart of our framework is this function, which is basically going to play a major role for the rest of our talk. So here, GXC it evaluates as the optimal value of a conic uncertain optimization problem, where the uncertainty is only going to live on the right-hand side over here. So you see that there is the recourse matrix B. It doesn't have anything to do with the uncertainty. And so you'll come to know very soon why we consider this model, because this is very flexible, and it's also, it can accommodate all kinds of constraint functions and 1-stage and 2-stage problems with different types of convexities. And at the same time, it also allows amenable I mean, it's amenable to tractable reformulations, which means, as we will show later, it's just because it's flexible, it doesn't become intractable. So that's basically flexibility and tractability all in one. So now, first I'll just try to talk about the modeling power of this. So this kind of why we chose G to be the optimal value of a convex optimization, uncertain optimization problem. So if you take biconvex functions, so if you take functions of this form, which are biconvex, so you have the x, the decision variable x, and the uncertainty parameter z. So this can be easily, just by a simple transformation, you can actually write it in the format which I just showed a few slides before. So you can see by conic greater than or equal to fx plus fxz. And so here you have the perspective cone, which preserves convexity. So biconvex functions can be handled. But it's not just biconvex functions, but even functions traditionally looked at in the robust optimization literature, which are convex in x, the decision variables, but concave in z. Even they can be handled by our model. So that's, for example, the saddle functions here. So for example, if you have a saddle function h, you could actually rewrite it in terms of f, which is basically the conjugate of the negative of h. So you take a conjugate of the negative of h as f, and then you take its conjugate again. So you're going to get this type of a formulation. But this reformulation is still not good enough for us, because as you see here, there's a v transpose z, and this is not in the format which we have, because here the v and the z, there is a product, whereas in our case the recourse variable is not in a product relation with the uncertain parameter. So that can be again handled, and as I've shown here by this minimax, Sion minimax interchange, you can actually bring out the v and make it as a first stage parameter, and as a result you can actually reformulate it exactly in the form which we have earlier, where the recourse matrix has nothing to do with the uncertainty. So this is this is something which we just want to show that we can handle those functions which are concave in z as well. And of course, if you have two-stage stochastic optimization problems, so when the cone k is the non-negative orthant cone, you could actually, this g of x is reminiscent of a second stage cost function, so we can also model these type of problems. So and it's not just these varied class of problems with concavity in z and convexity in z, but we can also tackle objective uncertainty. So if you have uncertainty in the objective, you could just use an epigraph variable, bring it down to the to the constraint, and you could actually reformulate it in our format. Or if you had multiple constraints, so let's say you had like gi of xz instead of gxz, so then you could actually use multiple parameters k over here. So you have this weighted sum of the robust satisficing measures here. So that can be used to model these kind of problems. So it's really a kind of a grand unification, you can say, because many of the recent problems tackled in the literature can be actually modeled using this type of the formulation which we have. So for example, biconvex linear or quadratic constraint functions, this has been handled way back in the 90s itself, or saddle constraint functions, we just showed that. Nonlinear biconvex constraint functions, like where you have you go beyond quadratic, you can have any nonlinear as long as it's convex, these type of constraint functions. Then you could have like what we call ARO, or adaptive robust optimization problems, where you have like here, this is a two-stage adaptive linear optimization models. This can be handled. And lastly, adaptive convex optimization models, where the recourse variable appears in a convex, in a nonlinear but convex manner in the constraints or in the objective. So all these can be actually kind of unified under this one, the g of xz formulation which we had. Now the question is, after all this unification, are we going to ensure tractability and feasibility? Because without that, there's not much point in going through all this. So here, first I'll start by talking about an exact model. So a model where we actually have an exact reformulation of the robust constraint. So here, if we consider quadratic constraints with quadratic penalty, and also quadratic uncertainty set. So something like this, where you have the G to be a quadratic constraint like this, and then you have the Euclidean norm for the penalty function, and you have the epsilon r here, which is basically the ellipsoidal uncertainty set, and the calligraphic z, which is the uncertainty support, is basically a superset of the ellipsoidal uncertainty set. And without loss of generality, we're going to assume that the baseline parameter z hat is 0 from now on. So what do the results which we have here are similar to that in the literature. So for the robust framework, when you have quadratic constraints and quadratic, the uncertain set, you actually know that we can reformulate it as an SDP, and we have a similar result for the robust satisficing framework. So when you have this extra term here, the K Z transpose Z, that can actually be accommodated. Oh, sorry. Yeah, so that can actually be accommodated along with this AXZ whole transpose AXZ, which comes out of this, and you can actually again rewrite it as a SDP constraint. But the bigger challenge is actually the feasibility. So we actually show that the feasibility holds for a target which is strictly greater than Z0, and the proof basically involves using the S lemma and the Skerr lemma. I mean, the S lemma and the Skerr's complement along with the Slater's point. So this is now the exact model. So in the exact model, we have this feasibility result. Now let's go ahead to a case where we need not have such an exact reformulation. So that's when you have polyhedral penalty. So when you consider polyhedral the uncertainty set, just before I go into the further details, let me just talk about what are the assumptions we have. Complete recourse, because without that we will not be able to use the duality techniques which we need, the strong duality with for the conic optimization problems. Second, as of course that's like the foundational assumption here, we have a polyhedral support. And yes, the penalty which we have now, that is something which, so earlier it was quadratic, now we have this form. So we formulate it in this manner, as you can see, as a max of lambda transpose z minus eta subject to this constraint. And the reason we do this is because this can actually help to model not just polyhedral norms, but it can actually go beyond polyhedral norms. So this kind of a polyhedral penalty function is what we assume in this part. So for example, if you consider a budgeted norm, like which computes the sum of the largest k largest absolute components of a vector, in this case gamma largest. So you can see that this can immediately be just by a suitable transformation, you can just write it in the form which we had in the earlier slide. So just to show how we could actually, and then of course when you take k equal to 0 or you take k equal to n, you're going to get back the one norm and the infinite norm here. So now we come to the crux of our result. So what do we do with this robust satisficing framework which we have? Okay, so this is what we have assumed now. So now with all these assumptions in place, this is the problem we have. You have conic inequalities and you have a polyhedral uncertainty set. So how do we deal with it? So typically now we can't use linear decision rules because you have conic inequalities here. And so although we have assured that there is a feasible solution because of complete recourse, we don't know anything about how it looks. And it's hard to say, yeah, I mean, what's the structure of the feasible solution, leave alone the optimal solution. So the main result involves dualizing this. So this part of the these two constraints here, and we dualize once over the recourse variable y. So this yz, which is basically the second stage variable, we dualize once over the y, and then the second time we dualize over the uncertain parameter. And this double dualization technique leads us to a formulation which now has betas and mu's and etas as the new set of recourse variables, what we call as the dual recourse variables. And the beauty of this is that now the conic inequalities in the primal formulation ends up in the dual uncertainty set, the new dual uncertainty set, and the linear nature of the polyhedral uncertainty nature set which we had earlier, the uncertainty support, turns up as the linear constraints in the dual. So essentially now we can use all the traditional, the techniques available, like affine recourse adaptation to actually approximate this. So tractability is we can always so by using linear decision rules, which is a subclass of the bigger class of all decision rules, we can actually assure tractability. So now that we have solved one problem, so let's just summarize. So what we did is basically we transformed the polyhedral uncertainty into a conic uncertainty set, and the conic constraints showed up as the linear constraints. So we have a robust linear program with a conic uncertainty. Now the proof is interesting, but in the interest of time, I'm not going into that right now. Now the bigger question actually is about feasibility, right? Because many times we can reformulate problems and get tractability, but feasibility is a challenge. So here, interestingly, we show that even though the primal problem, we didn't know how the feasible solution looks, the dual problem, this dual robust double dualized problem actually admits a very simple LDR approximation. In fact, a zero decision rule, as you can see here, beta and eta can actually be shown to be zero. There's a feasible solution which admits this. So that's quite interesting because considering that the problem originally, at least, it was not as simple, and it did not admit a zero decision rule. So now, what happens when we go to when we actually consider the non-negative orthant cone? So in this case, there have been results already earlier by Long Simenzo in 2021 itself. So this paper on the Tao of robustness, they actually talk about how when you have a two-stage adaptive linear optimization problem, you cannot guarantee that there will always be feasibility with linear decision rule, right? So the same problem which we considered, the robust satisficing problem, here's a simple example, a counter example where only a non-linear decision rule is feasible, right? So therefore, it's interesting to see what happens with our double dualized framework. So yes, so we had this result follows through. The nonlinear decision rule is certainly it's always feasible for the primal, but for the doubly dual formulation which we just showed, we already know that zero decision rule is feasible. So we actually show that a linear decision rule approximation for the dual is actually better than the primal NLDR approximation. Now, this is quite surprising considering that the LDR is simpler, but still it provides a better approximation than the NLDR approximation. So that means the dual is giving us, is adding value here. Now, then there are other things which we can say, like if G is a saddle function, then we could actually say that the double dual LDR approximation, we can actually show that it's the approximation is exact because this uncertainty set reduces to a singleton set in this case. Right, so now I conclude with the numerical part of our work. So we have three numerical examples. I'll start with the simplest case, the lot sizing example, which is where you have the non-negative orthant cone. And I think all of us are familiar with the lot sizing example. So I just quickly mention the assumptions we have. So in the first stage, we can order some the initial inventory, which is xi, and at a certain cost ci. And once the uncertain demand is realized, I can either transport yij between nodes I and j, that in our inventory of quantity yij, or I can order wi quantity at an extra cost, which is quite expensive, of li. So typically, so this lot sizing problem has been addressed earlier as well without this double dualized framework. So now let's try to see how this dual framework works. So this is the original problem, right? So this is just all that it's saying is the node constraints, the demand constraints are satisfied at every node. And so it's basically equivalent to this. You don't have to worry about all the math in here. All that I'm trying to say is there are even for the robust model, we can use the same dualization technique and you can get this dual robust model. Same thing you do with the robust satisficing, you get a dual robust satisficing model. So basically we have four models here, a primal and a dual robust and robust satisficing model. So so what's the point in having these four models? So one thing is, okay, let me first talk about the computational aspect here, and then I'll come to this. So it can be seen that the dual models, which are these bottom two models here, the blue is the dual robust and the red is the dual robust satisficing. they are much faster than the primal models, which are on the top here, right? So one thing is, in general, the dual models are much faster. This has been also observed earlier in some work. We actually retrieved those results, and in fact, it's quite a significant difference. And among the dual models, the dual robust satisficing model is even faster. Now, as far as the left-hand side, we are just computing the, we are just showing that the expected total cost, the out-of-sample expected total cost for a given first stage cost is when plotted for different values of the initial costs and the transport costs, the robust satisficing model, which is the red line here, it does much better in terms of this. So also just, as far as the computational time was concerned, just to understand why that is so, it's because if you look at the number of non-negativity constraints so this is like on the left side, you see the primal formulation, on the right side, you see the dual formulation. So you see that the affine constraints are order n cube over here, whereas here it's something like order n square. And as far as the non-negativity constraints and the decision variables, they're all order n cube on both sides. So what I'm trying to say is that the dual formulation has actually much less affine constraints, although it has slightly more non-negativity constraints. But the numerical solvers find it easier to handle the the non-negativity constraint, and that's the reason why it's faster. Now, the other example which we had was of a growth optimal portfolio example, where we actually are trying to maximize the expected log utility or to minimize the risk over there. What you see, the minus h. So, so essentially, what we do is we actually assume that, so for this uncertain returns, right, and for given portfolio allocation x, so we perturb the mean by a quantity z, and we assume that we know the mean and the covariance matrix for this. Now, when you actually write down the robust satisficing problem and the robust problem, this is how they look, right? So we are minimizing the worst case risk involved in this, and you can, this is exactly, it comes back to the quadratic example I earlier discussed. So you have quadratic uncertainty with quadratic, we assume the E epsilon r here, which is the quadratic uncertainty set with a quadratic constraint. So this can be reformulated as SDP, as we discussed earlier. And the results, basically the expected shortfall as well as the ruin probability. So the ruin probability is the, so we are basically, plotting here the expected log utility, the probability that this is less than 0, because if it is less than 0, then in the long run, the ruin is, so there is a probability that of ruin. So this, both of these actually clearly show that the robust satisficing model is actually doing much better in terms of both the expected shortfall and the ruin probability. And the last example I have is of the log sum exponential. So this is actually coming to the conic, like the conic constraint, which is like at the core of our work. So if you consider a two-term log sum exponential model, where you just have these two terms here, two exponential terms with Ri and Si matrices, which are randomly generated. So for this setup, you can actually reformulate this exactly in the form which we have with in the conic as the optimal objective of conic uncertain optimization problem. And this is the cone which we have. And the interesting thing here is that you have multiple constraints. So as discussed earlier, a model can accommodate these multiple constraints as follows. Like as you can see here, the ki's instead of just a single k, right? And then we are considering the weights to be unit weights here. So you just add up the k's. And in this case, what we plot is the violation probability and also the total expected shortfall. And what you see here is the range of values here. I mean, the 10th to the 90th percentile, that's what you see plotted. And the actual plot is the mean. And so we do this for a box uncertainty set. So a box of size R, that is the uncertainty set here. And the uncertainty support is basically the unit hypercube. So with this kind of a setup, we can also see that the robust satisficing model does much better. So, so basically, in conclusion, what we showed is whether you take the simple lot sizing example or whether you take the quadratic constraints or this kind of a general conic constraints, an exponential conic. So you can actually show that the robust satisficing model is doing much better. So in conclusion, it's again giving another example, just like we discussed about the rain in the beginning. So as far as protection is concerned, we could decide to not protect ourselves thinking that everything will be fine, or we could have a first aid kit which could give us limited protection. But taking an insurance policy, not just for health, but across all, in all our walks of life, so that's something which would account for the uncertainty, but it wouldn't also be too expensive. And that's, I think, the core of what we wanted to say, that at the similar costs, we are getting much better protection. So thank you very much. If there are any questions or comments.
Any questions? Time.
There is this some work of Dimitri and David Brown and Bental on the soft robust model. Is this sort of related to some of those things? Or?
So there is a relation with there's a relationship. Maybe is this mic working? Yeah. So there's a relationship in a plain sense, right? The soft robustness and the globalized robustness, they are all similar ideas, right? And that's also connected with what is that? The convex risk measures. So I think all these are equivalent. So in the deterministic uncertainty framework, you'll be this globalized robust. So what is globalized robust? It's actually the same formulation that you see, but the K is fixed. The K is fixed. So it allows the constraint to be violated, but the violation is controlled by some norm or some distance. Right? Now, my issue with those models is that there are a lot of parameters to choose from. Right? First, how do you choose this K? Right? It's not easy for you to choose this K. Right? How do you come up with the globalized robustness model to choose that? And how how it was related is that I at some point work on satisficing, so I come up with a decision criteria. So the idea when you have a decision criteria, it kind of it stems from how you make decisions. In this case, I choose target, and from there I axiomatized how I can make decisions using target. And turns out that there's a dual formulation with this convex risk measure. And when you come out in the explicit in one of the simplest form is just to put K as a variable to optimize and using target. So that kind of using target as a replacement of this parameter kind of helps to at least address those issues on specification for this model. So they're all kind of related. I think more interesting is that I didn't know that it works well, right? So I think what we have tried is that you look at the robust optimization where you restrict uncertainty set, right? You don't allow, you kind of believe that nature will only happen within the uncertainty set. That's where this first aid box, right? You do not know what kind of injuries that you're going to get, but you assume that injuries will be just, some simple injuries. So you bought a first aid kit that will protect against that. So you restrict nature, right? But nature could be far worse than just falling down. It could be heart attack, other things that the first aid kit couldn't address, right? And that's where you look at it in the robust in this robust satisficing, right? Allow nature to move, right, to be the entire support set. Right? And what you need to do is just to minimize the impact of uncertainty. So that's a different way of looking at the problem.
Okay. Any further questions? If no, we can end this session. See you tomorrow.